Thank you very much, and thanks very much to the organisers for the invitation to speak and for allowing me to stay a little bit longer as well. I was a postgraduate student at the session here in 1997, which is quite an exciting experience. I managed to see a lot of big famous names such as Walter Fite and Don Thompson at this, and it's fantastic to be back here as a speaker. Right, so I was asked to talk about conjectures in local representation theory. I guess there are sort of two broad groups in which most of these conjectures fall. One of them is if we know the defect group or something about the defect group, what restrictions can we put on a block of a finite group? And the second one is can we find more precise information about our block from local subgroups? I suspect the organisers really wanted me to talk mostly about the second, so I'm going to talk about the first today. Partly because I don't really want to disappear down the rabbit hole of notation, which is Dade's conjecture, and partly because a lot of my interests have been in the first half in recent years. But if anyone does want to know about Dade's conjecture, I am around to talk about it if you want. Okay, so I'm going to talk about what happens if you say something about if you fix your defect group or fix some aspect of your defect group. What can you say about your block, or what restrictions does it put on this? So I'll just fix some notation from the start, or say what some symbols will usually mean. So usually, always, G will be a finite group. Now we're going to take a p-modular system. The choice of this isn't so terribly important at the start, but in general for most of these conjectures. But when it comes to talking about Donovan's conjecture, I want to make a fixed choice so that we at least have a canonical statement of a conjecture. So we can think of K as being the algebraic closure of Fp, and O being a ring of bit vectors with respect to this. I mean, there are a couple of ways to state Donovan's conjecture for O. I think we're more or less deciding on this one now. Right, B will usually be a block of OG, as described by Marcus Linkelmann, but it could sometimes be a block of KG, and hopefully it'll be obvious from the context which we mean, but I want to write KB as a shorthand for the block of little k when necessary. I'll fix, D will be a defect group of B. So if you recall, the defect group is in some sense measuring the distance from semi-simplicity of your block. So blocks of defect 0, these are semi-simple algebras, whereas on the other hand, the principal block, the one to which the trivial representation belongs, has defect groups for Zelov p-subgroups. Okay, and so we do expect the defect group to somehow encode a reasonable amount of information about your block. So in some specific cases, we can deduce a lot of information about our block. So it's been known for quite a long time that if D is cyclic, then you can have very precise information. We can talk about the irreducible characters and the simple modules, and we see that the Morita equivalence classes are somehow given by Brauer trees. And similarly for in the tame for tame blocks for when D is dihedral, semi-dihedral, or generalized quaternion. Karen Erdmann has given very nice descriptions of these blocks. And there are other cases, as you heard yesterday from Cesare Odito, is talking about a case when you have an elementary abelian 2 group as your defect group. You can, at least in the small cases, you can say precise information about your block. So you have these cases, but I'd rather really here talk about general conjectures and results, which you can say across defect groups. Okay, so, well, as a slight motivation, I say we know, well, we have this Brauer-Feit theorem, which I think was from 59, that the number of irreducible characters in a block is bounded quadratically in the size of a defect group. Quarter, isn't it? So we have a quadratic bound already. So already the defect group is exerting some influence. So Brauer went on to conjecture, I should say about Walter-Feit. So one of my strong memories from this conference in '97, sitting around at coffee time with a bunch of other postgraduates, and Walter-Feit came along and stole one of our biscuits, and we were starstruck. Walter-Feit stolen a biscuit! Right, Brauer's conjecture. This is Brauer's KB conjecture. And this simply states that we should have a linear bound, and in particular, we should have a particular nice linear bound. Okay, so we can't do any better than this, because we could just take G to be an abelian P group in the start. And this conjecture is quite resistant to attack in some ways. So it's difficult to reduce in general. But where early progress was made, significant progress was in the case where we just take p-solvable groups. Okay, so very quickly, Nagao realized that for p-solvable groups, this is equivalent to quite a restricted-looking problem, but turns out quite a hard one. So for p-solvable groups, it's equivalent to the KGV problem. Okay, so this does have some recent interest, despite being solved a little while ago now. And this is that if G is a p-prime group and V is a faithful FP G module, then the number of conjugacy classes of a semi-direct product should be at most the size of V. Okay, so I showed that this was an equivalent problem, or equivalently you could choose V to be irreducible as well. And this was, this turned out to be really hard and to involve the classification of finite simple groups. So this was solved. Oh, okay. Let's finish this blackboard. So it was solved in '04. Well, after a lot of work. So Knur made important contributions to this, reinterpreted by Gao, and then you have Robinson and Thompson, and then restricted the primes for which you have to look at. And then there was this massive effort of picking off various primes a few at a time. So we have contributions from Köhler and Parlings and Goodwin. As one of Martin Liebeck's students, and until it was finally reduced down to checking p equals 5, and this stood for a little while in the early 2000s. And it was finally finished off by two sets of people simultaneously, Gluck and Maggard. And we have Udo Rieser and Peter Schmidt. So I didn't know Kai at the time, so I was in the Rieser Schmidt camp because I knew Udo at that time. And so they solved this independently but decided to write it up together as a paper. But yeah, an immense amount of effort by a number of people there. Okay, so I should talk a little bit about what the other progress this has made, but in general this is actually done in cases where we know a little bit more. We have fairly detailed information about the blocks anyway, and this is somehow a byproduct of this information. So in terms of actual results, where we're proving something general about the about the KB conjecture, it's fairly resistant to attack. But I don't want to dismiss the immense number of cases which have been done for this. Okay, so another related conjecture. Well, we observe trivially that the number of simple modules is at most the number of irreducible characters, and so L of B, we expect L of B to be bounded by the size of a defect group 2. But can we think of a better bound than this? And so it was actually only quite recently that this was attacked. Okay, so we have this conjecture of Mallow and Robinson. I guess it's appeared in 2017. And that we expect that the number of simple modules to be at most P to the so-called sectional rank of your defect group. So, so P to the SD is going to be the size of your largest elementary abelian section of your group, i.e. Quotient group of a subgroup of D. Right, so it's the rank of largest elementary abelian section. Okay, so as you can imagine, in a paper by Mallow and Robinson, they cleared up lots of quasi-simple cases, but they also looked at this for p-solvable groups, and you can also reduce this to the KGV problem, and so it is true for p-solvable groups. So for p-solvable groups, it's equivalent to KGV problem. So it's true. Okay. So in this, you implicitly, this means that we've got to use it for classification of finite simple groups. Okay, how else can we modify this? Well, one direction was by Olson. Can we say anything about irreducible characters of height 0 as appear in the Alper and Mackay conjecture looked at by Britta? So the height of an irreducible character the height h of chi is defined by okay, so we always have an irreducible character of height 0, so its p part is the same as the p part of the index of d in G, but it can be a little bit larger, so it's a number we need to multiply this by to get up to the degree of, or p part of a degree of chi. I hope that's right. Yep. Okay, so particularly we're interested in height 0 at the moment, and so we have Olson's conjecture. So I think it was 84. So the number of irreducible characters of height 0 should be bounded by the size of the derived quotient, or the abelianizer. Okay. Okay, so similarly to Brauer's conjecture, this is a little bit resistant to attack. Okay, so since I'm trying to be fairly comprehensive in this, it doesn't fit quite into the same pattern, but we have Brauer's height 0 conjecture. It's been a highlight of recent years. And I offer a few reasonably recent remarks to make about this. And this is simply that D is abelian if and only if every irreducible character in your block has height 0. So D being abelian or not is expected to put some restriction on what's going on in your block. Okay, and so this is true for p-solvable groups. Okay, so another of these results where it's perhaps harder than one might naively expect. Right, this direction is pretty immediate. It's a simple exercise using elementary facts about p-solvable groups and Phong correspondences. So this is true by Phong in 61. And the other direction requires for classification of finite simple groups. So this was done by Gluck and Wolf. When was this? 84 as well. Okay, so it's using the classification of finite simple groups. I think it's actually quite a nice paper. It reduces quickly to a very simple statement, a very reduced situation, which you think, well, this looks easy, but then you have to have a full might of classification of finite simple groups, not in particular to consider those automorphisms of order P of a simple group of order not divisible by P. In general, this direction was known by, after a lot of work by a number of people, and finished off with a final massive effort by Kessar and Mahler. Which was published in 13. Of course, using the classification of finite simple groups. So this required deep understanding of the blocks of finite groups of Lie type in cross-characteristic, and it was an analysis of a quasi-isolated case to get the final cases. So there's a lot more in this paper besides verifying this conjecture. And the other way, well, okay, I should say that the reduction for this direction was done by Berger and Knurr a number of years ago. Reduction in the other direction is harder, and a reduction was done by Navarro and Speth in 14, and it's reduced to, well, checking this conjecture for quasi-simple groups. For quasi-simples. Plus the inductive form of the Alperin-Mackay conjecture. This is a slightly different form of the Alperin-Mackay conjecture to the one that British presented, which was the non-blockwise version, if I remember right. This is the blockwise version, of course, for simple groups. And in their paper, they knocked off this. This was done by Kessar and Mahler in 17. Okay, so we know this part, so it remains to the very knotty problem of verifying this for simple groups. So that's where we are with the height zero conjecture. Okay, so I should mention there is an extension, so we can make, if we define the minimal non-zero height of a block to be, well, the minimal non-zero height of an irreducible character in B. So and we're going to define it to be, okay, this is nasty in a way, but it's convenient. We're going to define it to be in infinity if there aren't any height zero irreducible characters. Positive height characters. Okay. And so we might conjecture that this number is equal to the corresponding number for the defect group. So here we're treating, we're really considering the block KD or OD. Okay. Okay, I've got time to talk a little bit about this. So, in a sense, this is a generalization of the height zero conjecture. So we have, we consider this way round, then, okay, so if, we got this around the right way? I'll do it around the other way first. So we consider it this way round. So if D is abelian, then well, we have no positive height irreducible characters. So this is infinity, and so this is infinity as well. So we have no positive height irreducible characters. So this is a generalization of. Shouldn't change the order of my notes. It's a generalization of this direction of height of the height zero conjecture. And of course, vice versa. Okay. And so, similarly, for p-solvable groups, one direction is easier than the other. So this direction is true for p-solvable. So you can prove this without the classification. Well, okay, you can prove this. Of course, it doesn't need the classification. You can prove this directly, or you can observe that this direction is as a consequence of Dade's projective conjecture, and we know Dade's projective conjecture for p-solvable groups. But that's a much harder way around of doing it, given how hard it is to show Dade's projective conjecture for p-solvable groups. Of Dade's projective conjecture. Okay, so as with all of these things, this is being checked for a bunch of examples. I must say I'm not entirely confident about the equality in this. Obviously, this direction, this inequality is pretty solid as being a consequence of Dade's conjecture. We thought about equality because, well, we're looking at so many examples, and it wasn't looking like we could get a strict inequality. Right. Okay, so I want to move on to the meat of the talk. What did we decide about this one? But oh yes, it gets moved up eventually, and you guys know about it anyway, so that's just fine. So okay, so we could Donovan conjecture. So this comes from from one of Brauer's problems, where he asked the question: are the Cartan invariants of a block bounded by the size of a defect group? Okay, so that turns out to be true. To be false. That particular. Oh, I think someone appeared at the back of the lecture theatre. A little light's gone out on my speaker. Can you still hear me? Yes, fine. Okay. I think the battery's run out on this. Okay. Okay, so what was I saying? So this is inspired by a problem of Brauer, where he tried to give an explicit bound on the Cartan invariance of a block. That turned out to be false. Peter Donovan was more bold and expressed this as a conjecture. And this is that the largest Cartan invariant CB of B is bounded in terms of a defect group. Okay, or the size of D, if you want. So largest Cartan invariance is the largest entry in the Cartan matrix. Okay, so should we remember this is the thing which records the number of times a given simple occurs in a given projective indecomposable module. Okay, so this is really an object which is living in the world of little k. Okay, so I want to make a few remarks about this because this conjecture takes on increased importance. So first of all, because of Brauer fight, we have a bound for the number of irreducible characters in terms of a defect group. We also have a bound for the number of simple modules of a defect group, i.e. the size of your Cartan matrix. So this is equivalent. Oh, okay, and the dimension of a basic algebra for your block is the sum of all the entries in your Cartan matrix. Okay, so this is equivalent to bounding the dimension of a basic algebra. So bound for the dimension of a basic algebra for blocks with defect group D. Okay. Also remark that Olaf Dufel, student of Gerhard Hiss, he proved a bunch of reductions for Donovan's conjecture and a weak Donovan conjecture, and so he reduces this to quasi-simple groups, or quasi-simple groups with center not divisible by P. Okay, and the third remark I want to make is that because we're going to want to really be serious about solving the weak Donovan conjecture, I'm going to split this conjecture into two. And so we observe that the largest Cartan invariant can be got from the Lovie length and the largest dimension of an X space between two simple modules. So it's going to be, okay, so explicitly, okay, this formula doesn't really matter. But my statement before is the important thing. Okay, so we can get this largest Cartan invariant in terms of, oh no, B, yes, L of B. Okay, where this is a Lovie length. Okay, so we have our projective indecomposable modules. Okay, and we can write their Lovie structure. So we're taking a succession of radicals of these modules. So it's a bunch of big block of simple modules. Okay, the Lovie length is its height, and this is going to go some way to governing how fat this big block of simple modules can be. So this is going to be the largest of the dimensions of the A's X spaces, X1 for B for two simple modules. Okay. So weak Donovan is equivalent to so bounding E of B in terms of D plus bounding for Lovely length. Okay, so I just want to make a couple of remarks about these. Okay, so this relates back to a conjecture of Graulich, who first thought that, okay, if one of these simple modules is the trivial module, then we ought to be able to bound the dimension of these X spaces, well, he said by an absolute bound. Of course, the absolute bound he initially conjectured turns out to be false, and now it's thought that probably there isn't going to be an absolute bound. But we don't care about that. We only want to be able to bound this thing in terms of the defect group. So we can refer to a body of work relating to the thread which Graulich started. So see work dating back to a Graulich conjecture. So I want to particularly pick out Graulich's, Partial and Scott. Who addressed this for groups of Lie type in defining characteristic. And I would also want to mention some work of Graulich and Tiepp, and Harrison Parker and David Stewart. Okay, and well, this is less relevant, really. We tried to get some precise bounds on the Lovely lengths in some situations. So we've considered the case where D is abelian and conjectured some bounds. So this is a paper with Michael Leavesey from 17. Okay. Okay, so checking for weak Donovan conjecture turns out to be really hard and relevant, as we're going to see in the final third of this lecture. So any help we can get is appreciated. So be able to tap into this work of Graulich is an important thing. We have very little idea of how to bound the Lovely length, and I think it's a problem worth investigating. Will you remember that G is a finite group? I can rub it out. Right, okay, so we've already heard Donovan's conjecture. And essentially this is that we should stop messing around trying to bound invariants. Let's just go to the object which is at the heart of everything, the Morita equivalence class. And this can be stated over O, over K, or O. I think Dave Benson has spoiled this for me. I was calling it the O'Donovan conjecture, and he pointed out that this sounded like someone from the other side of the Irish Sea. So fix a finite group P. Then there are only finitely many Morita equivalence classes of blocks with defect group isomorphic to P. I realise I've been rather tighter in my notation for choosing D isomorphic to P than I have in previous conjectures, but never mind. Okay, so if we can show that there are only finitely many Morita equivalence classes here, well, we know that the Cartan matrix is a Morita invariant, so we automatically get the weak Donovan conjecture. Okay, so when I first started looking at this, I thought, well, maybe it's true, maybe it's not, I don't know. It's somehow solidifying, in my mind at least, but this is something we expect to be true. So I think one of the most important advances in this has been the recognition that we should split this into two conjectures by looking at the gap between this and the weak Donovan conjecture. And so we do this as follows. So this is done by Kessar. So he's looked at the gap between Donovan and weak Donovan. Okay, and so we do this as follows. So we consider the following ring automorphism where we just raise the coefficients of our group elements to the p power. So we take a Frobenius automorphism. Okay, oops. Okay, so we now have a ring automorphism, but not necessarily an algebra automorphism. So we're going to get a permutation of the blocks because we're going to permute the primitive idempotence of a center. So this permutes the blocks. Of Kg, and then because blocks of OG correspond to those of Kg, we have a permutation of the blocks of O as well. Okay, and we can ask the question. Well, okay, we have a finite number of blocks in a given for a given finite group. So eventually, after repeating this automorphism a number of times, we're going to come back to our original block, but we might come back to a block which is Morita equivalent to our original one a little bit earlier. So we can ask, well, if we assign the invariant the smallest number of times we need to do this until we get to a Morita equivalent block, we can ask, is this bounded in terms of the defect group? So we define the Morita Frobenius numbers. Oh, I haven't got room for that. So MFK of KB, so definitely talking about a block with respect to the field, is going to be the minimum of M, at least one, such that sigma applied m times to KB is Morita equivalent to KB, and we have a similar number over O. Okay, so we note that MFO may be arbitrarily large by work of Livesey from just recently. But as yet, we only know of examples for K, Morita Frobenius number, at most 2. This was something which caused quite a bit of excitement back in, I guess, 2006, when it was realized that the Morita Frobenius number didn't have to be 1 by work of Benson and Kessar. It's quite an exciting overall fact to be at, where the method was identified as to how this could be done, and it just needed to find groups which actually implemented this. Right. Okay, so the important theorem here, so the reason I've introduced this is that it allows us to split the conjecture up into 2. So this was due to Kessar. And Livesey. So myself and Florian Eisler and Michael Livesey, I guess this is 18. This is for K. This is for O. But Donovan's conjecture is equivalent to the weak Donovan conjecture plus bounding in terms of D. Okay, so essentially, so this direction is obvious. These are both going to be Morita invariants, Cartan invariants, and the Morita Frobenius number. But the other way, less trivial. And the way to look at this is weak Donovan conjecture, as we saw before, is really bounding the dimension of a basic algebra. Okay, so this is the intuition over K, a little bit harder over O. Okay, and this bounds the field of definition of a basic algebra. Okay, so if you can do this, then you're saying, okay, you can represent your basic algebra by restricted size matrices, and here is the structure constants are going to be in this field of restricted size, and so there can only be finitely many isomorphism types of these algebras, even though that number is going to be colossal. Okay, we have got a theoretical bound on them. important thing here is that these Morita-Frobenius numbers, and in particular the O Morita-Frobenius numbers, are quite amenable to reductions. So one thing with the O Morita-Frobenius numbers is or rather, a slight alteration called the strong Morita-Frobenius number. We can treat these as being very similar in this context. Is that they allow you to get past a knotty problem of descending to normal subgroups of index P, okay, which is really tough. So we're able to do that at least in the abelian defect group case, and a slight generalization of that. And for weak Donovan conjecture, as we already saw, is particularly amenable to reductions. We already know it's reduced to quasi-simple groups. Okay, so we have theorem, which is a combination of a reduction result with Leavesey and Florin-Zeller, and work of Farrell and Kessar. I guess this is all probably from around 18, where they proved that the Morita-Frobenius numbers are bounded for all blocks of quasi-simple groups. And so we're able to show that Donovan's conjecture for abelian defect groups is now equivalent to a weak Donovan conjecture for abelian defect groups and quasi-simple groups. Okay, so essentially, so what Farrell and Kessar do is that they sort out the right-hand side in the well, in general for quasi-simple groups, but we're interested in the abelian case for quasi-simples. So we sort out the right-hand side after some reduction, and then we're just left with a weak Donovan, and that's already reduced to quasi-simple groups. And so we have that. So I should say, so as a direct consequence of this, we know that Donovan's conjecture holds for abelian defect groups, for abelian 2 groups. So this is using an earlier classification with Kessar, Kuhlsammer, and Sambala. Hammer and Sambala from 14, where classified blocks of with abelian two blocks of abelian defect groups of quasi-simples, and in particular verified for weak Donovan. Okay, so I should say that general progress on Donovan's conjecture is held on a website which Marcus and Cesare told you about in their talks. So that includes progress on Donovan's conjecture and also about classifications of blocks of a given defect group where we can achieve this. So this is very much work in progress. So it's not complete, although the progress on Donovan's conjecture is complete. Okay, so what else do we know? I should say other progress on Donovan's conjecture. Of course, we've known this for cyclic defect groups for a long time. Most tame blocks over little k But there's this famous missing case of generalized quaternions with two simple modules. But there has been some progress on lifting these results up to O. So some work was done by Holman, Kessler, and Linkelman, and then Florian Isola worked on a generalized quaternion case for three simple modules, lifting these results up to O. So you have Donovan's conjecture in those cases. We know this for p-solvable groups, going back to work of Pooch. And another theme is to, well, you restrict your attention to a class of groups, say some particular groups of Lie type, and trying to show Donovan's conjecture within these. Okay, I've got a few minutes. I just wanted to talk about one little thing, which I really like, not related to the previous stuff. And just because I want to highlight it. So also, we have this conjecture of Mahler and Navarro. Okay, so one might ask, one might ask, what can you tell about a block from the character table? Okay, and there are a number of results and conjectures along these lines. But one particularly niggly one is, okay, you take nilpotent blocks, as described in Marcus Linkelman's talk. So these are ones for which the fusion is the same as the fusion just of the defect group acting on itself. Okay, we know a lot about these by work of Brauer and Pooch, and particularly we know that all the height 0 irreducible characters have got the same degree. Okay. The main thing about nilpotent groups is that they're Morita equivalent to the defect groups, but we have this result. And so we could ask, well, does this characterize these blocks? So is it true that B nilpotent is characterized by every height 0 character having the same height, same degree. Okay, so this has been verified in a bunch of quasi-simple cases, as you can imagine, and reduces to quite a knotty problem in group actions for p-solvable groups. So it's not even known for p-solvable groups, as far as I know. I think I'll leave it there. About the numerical conjecture, you said you're not so confident about the other side. Okay, that was a moment of over-honesty on my part. You said, okay, one direction is consequence of gauge. Yeah. But the other direction also is a consequence of OWC, of the ordinary wave conjecture, and something only involving fusion systems. All right, I didn't actually know that. Yeah, so, okay. I think. So right. Maybe it's good to try some fusion systems and see, assuming the counting conjectures, and see whether the fusion system, the prediction for fusion systems is satisfied. Right. That would be a way to have. Oh, okay. All right. Oh, that'd be really interesting. Yeah. So that's good because yeah. Because just you said that looking at the gap between Donovan and Brauer. I really got the idea from Gerhard. Okay. Yeah. Sorry.